let's begin a chapter that is chemical bonding. Firstly, I would like to make you aware about the significance of chemical bonding in chemistry. Whenever we enter into the field of chemistry, that means whether we talk of physical chemistry or organic chemistry or inorganic chemistry, it's a true fact that we deal with a chemical reaction. And a chemical reaction involves the association and the dissociation of bond. So, in chemistry, chemical bonding has got a vital role. So let's discuss what does this chemical bonding mean. So before starting the chapter, I would like to make you aware what does the word bond mean. So basically bond is an attractive force which holds species together. So the very first point about a bond is, so bond is an attractive force that holds species together. Like if we talk of solid substances, what we observe that the constituent particles of a solid are closely packed to each other. What does this close packing represent here? That every atom in this packing, they are held to each other through a force, and that force is called a bond. So now we can conclude a bond as a force which holds or bonds species together. Going ahead, we have now the another word, bonding. So as we are observing in this example that the species are held to each other, that means firstly the atoms or the species, they approach each other and then they are bounded to each other through a force which we call as a bond. So basically for the formation of a bond, the species should be approaching each other. So bonding is the phenomena which signifies the approach of the particles or the species towards each other for bonding with each other. So now bonding can be explained as an approach between species such that they should combine to each other. So in chemical bonding we have the word bonding. In bonding we had talked firstly about the bond, which is basically a force which bonds the species together. Second, we had the bonding word which represents the approach between the species after which they combine to each other. Now moving ahead, a question comes, why the species undergo bonding? Means why the species they try to combine to each other. So the question is cause for bonding. Why substances, why species required to undergo bonding? So the very first reason behind the bonding is that during bonding, when the species approach each other, there is decrease in the energy, and decrease in energy increases the stability. So for the cause of bonding, reason is decrease in the energy and hence increase in the stability. So we can summarize here that species undergo bonding to decrease energy and increase stability. Now let's check out how does this happen, how during bonding energy is decreased and stability is increased. Let's see here how during bonding energy is decreased and stability is increased. Now let us consider two uncharged particles. Let us call it as case 1 for uncharged particles. Now let's say the distance between, that is the internuclear distance between these two particles is given by L. Now dear student, as it's well known to us that potential energy for uncharged particle is given by the formula mass into acceleration due to gravity into separation between the two particles. Here m is the mass of the particle, g is the acceleration due to gravity, and L is the separation between the particle. As we have already discussed that during bonding species approach each other. That means for bonding, when particle A will approach particle B or vice versa, then the separation between the two, that is L, will decrease. Now if L will decrease, that means potential energy will also decrease. Now we know that the total energy is given by the formula kinetic energy plus potential energy. So we can say that if potential energy of the system decreases, that means that will decrease the energy. Now energy is inversely proportional to stability. So when particle A will approach particle B, there will be decrease of separation, that is length between the two, that will decrease the potential energy, which in turn will decrease the energy. So now we can conclude here that during bonding L will decrease, so potential energy will also decrease, that will decrease the total energy, leading to increase in the stability. So the very first fact that bonding decreases the energy and increases the stability can be verified through this given data that when particles will approach each other for the purpose of bonding, they will undergo decrease in their internuclear distance, that is separation, which in turn will decrease their potential energy, decreasing the energy and hence increasing the stability. Now let's come to another case, case 2, for charged particles. Let us consider two atoms which have nucleus at the center and electrons revolve around them in a fixed orbit. Let's call this one as atom A and this one as atom B. Now let's take their internuclear distance as R, basically it is the gap, these two atoms A and B. Now when they will undergo bonding, these two atoms will be approaching each other. So again, similar to the uncharged particles, when A and B will be approaching each other for bonding, R will be decreasing. Now in case of charged particles, potential energy is given by the formula minus K into Q1 Q2, let us call it as QA QB, upon R, where K is some constant. QA here is the charge associated with the particle A, QB is the charge associated with the particle B, and R is the separation between the two. So again, when these two atoms will be approaching each other, the value K into Q1 into QB upon R square will be increasing because R is decreasing. So when K into Q1 A into QB upon R square will be increasing, so we have got a negative sign before it that signifies the decrease of potential energy. So when A and B will approach each other for bonding, the distance or the separation between the two will decrease, again leading to decrease in the potential energy and hence decrease in the total energy. Besides this, the force or the attractive force between A and B is given by the formula K into Q1 A into QB upon R square. Here, due to the approach between the two particles, R will decrease, and as R decreases, F will be increasing. So we are observing that in case of charged particle, both radius or internuclear distance and energy between or energy of the system decreases, increasing the stability, as well as the attractive force between the particle increases, increasing the stability. So the overall conclusion is that during the approach between A and B, R will decrease, hence potential energy will decrease, total energy will decrease, attractive force between the particle will be increased, and hence stability will be increased. So whether we talk of charged particle or uncharged particles, when they come closer to each other for bonding, there is decrease in the separation between the two, and hence the total energy decreases, increasing the stability. Now let's move to another reason for the cause for a bonding. The second cause for the bonding was given by Lewis as Lewis concept. Now before understanding this concept, I would like to introduce you with the noble gases or inert gases which belong to the 0 group or the 18th group of the modern periodic table. In the 18th group of periodic table, or as I called it as 0 group, we have got helium, neon, argon, krypton, xenon and radon. Here helium has an atomic number of 2, neon 10, argon 18, krypton 36, xenon 54 and radon 96. Now these elements are the part of 18 or 0 group of the periodic table. Now let's observe their valence shell electronic configuration. For that, we can refer to the method of electronic configuration in the chapter atomic structure. Now helium has a configuration of 1s2. Neon has a configuration, valence shell configuration as 2s2, 2p6, argon 3s2, 3p6, krypton 4s2, 4p6, xenon 5s2, 5p6 and radon 6s2, 6p6. Now dear student, with an exception of helium, if we observe the valence shell configuration of neon, argon, krypton, xenon and radon, we can conclude that their valence shell configuration is ns2, np6, where n represents the valence shell of an atom. In case of neon, we have got 2s2, 2p6 in the valence shell. In case of argon, we have got 3s2, 3p6 in the valence shell. In case of krypton, we have got 4s2, 4p6. In xenon, it is 5s2, 5p6, and in radon, it is 6s2, 6p6. So in general, the conclusion is that in case of inert gases, that is 0 group or 18th group element, we will have the general electronic configuration of the valence shell as ns2, np6, where n represents the valence shell. Now the question is, why we call these elements as inert gas? Reason is that these elements possess a stable configuration and hence low potential energy and hence more stability. That means they do not undergo chemical reaction, they are less reactive, and this is the reason why we call them as inert gas. So now moving ahead, we can say that if an atom or element attains noble gas configuration, that is NH2NP6 configuration, then we can say that those elements will get stabilized. So let us consider an example where we shall be talking about NaCl molecule in which sodium and chlorine have been bonded to each other. Now let's check out that NaCl is a molecule in which sodium and chlorine atoms are bonded to each other by the loss and gain of electron, which we will discuss further just for the sake of understanding that how or what kind of configuration an atom can attain after bonding, that we are looking here. Else more details will be found in the later part of the chapter. So here sodium has an atomic number of 11, chlorine has an atomic number of 17. Now sodium will undergo the loss of one electron forming Na plus, and Cl will gain one electron forming Cl negative. Now if we observe the initial configuration of sodium, it is 1s2, 2s2, 2p6 and 3s1, where that of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Here in the valence shell of sodium we have got 3s1, whereas we have 3s2, 3p5 configuration of chlorine. Now when sodium will undergo the loss of one electron, it's obvious that electronic loss will take place from the valence shell. So its new configuration will be 1s2, 2s2, 2p6. While in case of chlorine, after gaining one electron from sodium, its configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. Initially it was 5, now one electron has been added, so it will be 3p6. So if we observe the valence shell configuration of sodium and chlorine, it is resembling to NH2 NP6 configuration in both the cases. So now we can conclude that during bonding, species attain inert gas configuration and hence get stabilized.